So we've done 2 rose graphs by hand, and you can see that it was a lot of work, and we plotted a lot of points, and we were connecting them as we went. Maybe now we should start looking at patterns here. So what did we notice as we were doing this? Well, first of all, we noticed that this number in front of the cosine told us the length of each petal, 4 units, 4 units, 4 units. Okay, and then when we had a 3 theta, we wound up getting 3 petals, and we only had to go 0 to pi to get the complete graph, and then it just would repeat itself after that. When we graphed the first one, though, that was a 4 cosine 2 theta. We still had 4 was the length of each petal, but with a 2 theta, we wound up getting 4 petals. And we had to go all the way from 0 to 2 pi to get our complete graph before it started repeating. So maybe we should look at a few more, except we don't want to graph these by hand anymore. So let's use some technology to help us. So we're going to plot a whole bunch of points for r equals 4 cosine 4 theta, and if we connect them as we go, we're going to wind up getting this graph. And notice, how many petals do we have? We wound up getting 8 total petals on there. So the pattern still seems to be holding here. The 4, the number in front, is the length of each petal. We go 4 units out for each petal. But with a 4 theta, we wound up getting 8 petals. So when we had a 2 theta, that gave us 4 petals. And when we have 4 theta, we had 8 petals. So it seems like if it's an even coefficient of theta, that we wind up getting twice that many petals on our graph, but we have to go 0 to 2 pi in order to get the complete graph. When it was an odd coefficient, 3 theta, we only got 3 petals, but we only had to go 0 to pi to get our complete graph before it started repeating itself. So let's try another odd one. We could do 5 theta, but how about if we do 1 theta? 4 cosine 1 theta. And we'll keep the 4s, so the length of each petal should be 4. 1 is odd, that means we should only get 1 petal. So let's see what happens. It's going around and around, and stop. What did we get? Well, we did get 1 petal, but notice this actually looks like a circle. And the diameter, so the length of the petal is 4, but that would mean the diameter of the circle is 4, or the radius is 2. Well, let me prove to you that this is actually a circle. So we have r equals 4 cosine theta. And I remember those conversion equations to go from polar to rectangular, or vice versa. So how about if I multiply both sides of this equation by r? Then I get r squared equals 4r cosine theta. And parts of that should look familiar. R squared was x squared plus y squared when we converted from polar to rectangular. And then r cosine theta is just equal to x. So what can I do with this? Well, how about if I rearrange it a little bit? Let's move the 4x over with the x squared. And then I'll leave a little space. And then equals 0. Why did he leave a little space? I don't know. Because I feel like adding 4 to both sides, maybe? Why is he doing that? Who knows? Oh, wait a minute. I can complete the square now. That's a perfect square. That's x minus 2 quantity squared plus y squared. Or, if I wanted, instead of writing y squared, how about I write y minus 0 squared equals 4, but I could write 4 as 2 squared. What am I doing? Why is he writing it like that? Well, that reminds me of something that we did a while back. X minus h squared plus y minus k squared equals r squared was the equation of a circle. And the center of that circle is hk. So for our example, the center would be 2, 0. And that is exactly where the center would be at 2, 0. And the radius equals 2. So the diameter was 4 and the radius is 2. So when we wind up getting just a 1 theta, it's a circle, or a rose of 1 petal, and the diameter is 4, the length of the petal is 4, and the radius would be 2. So let's summarize all this stuff. So if we have r equal a sine n theta or a cosine n theta, a will be the length of each petal. If the coefficient of theta is odd, so if n is odd, we'll get n petals, but we only need to go 0 to pi to get the complete graph. And if the coefficient of theta is even, we'll get twice that number of petals, but it's going to take us 0 to 2 pi to get the complete graph. So you're probably wondering, well, every example that we've done has been a cosine equation. What if it was sine equation? Does all this stuff still hold? Well, there's only one way to answer that, and that's to go ahead and graph each of those by hand, by making a table. No, we don't want to do that. So let's go ahead and use a graphing calculator. And I make sure that I'm in polar mode. I am. So I put these equations in. So let's graph these one at a time. Now, I want to point out that I set my window to go 0 to 2 pi. So I had to set it the same for all of these. So now when I graph 4 sine 1 theta, what are we going to get? Well, the coefficient of theta is 1, so we should get 1 petal, i.e. we should get a circle, and 4 is going to be the length of the petal or the diameter of the circle. And sure enough, notice it went around twice. Well, that's because the coefficient of theta, n, is 1, which is odd, so I only had to go 0 to pi. So as I'm going around, by the time I get to an angle of pi, I'm back to where I started. And so the window was set to 2 pi, so it went around another time again. The only difference, though, is this seems like it was rotated. Because when I did 1 theta for cosine, it was on the positive x-axis or the polar axis. This seems to have been rotated. That circle got rotated up 90 degrees, or pi over 2 radians, counterclockwise. Keep that in mind. We'll talk about that in a minute. So what if I do 4 sine 2 theta? Well, now the coefficient is even, 2. So we should get twice that many leaves. We should get 4 leaves. And it should take 0 to 2 pi to graph. And sure enough, 1, 2, 3, we get 4 leaves. But notice it didn't start on the polar axis or the positive x-axis. Once again, that first petal has been rotated counterclockwise. But instead of 90 degrees, let's trace this. It looks like maybe 45 degrees, or pi divided by 4. And sure enough, it got rotated 45 degrees. And that's when we had 2 theta. Keep that in mind. Let's keep going. So we're trying to see if the patterns that we came up with when we had all cosines is still holding for sines. And when we do sine of 3 theta, 3 is an odd number. That means we should get what? 3 petals, and it should only take 0 to pi. So there's 1, 2, 3. And notice because I went 0 to 2 pi, it went around them again. So that seems to work as well, except that first petal, once again, is rotated off the positive x-axis, or the polar axis. And how much was that rotated by? Well, it looks like less than 45. I think it was 30 degrees. So that's pi divided by 6, since I'm in radian mode. Sure enough, 30 degrees rotated up. All right, let's try one more. Let's look at 4 theta. So let me graph that one. Once again, the coefficient of theta is even. We should get twice that many petals, so we should get 8 petals, and it should take 0 to 4 pi. 1, 2, 3, 4, 5, 6, 7, 8. And that first petal was rotated up. So let me trace that. And how much was it rotated up? Well, this was a 4 theta. And what would be, I don't know. How much is that rotated up? Less than 30. Let me try something. Let me type in pi divided by 2 divided by 4. Sure enough, there's the tip of that first petal. So what did I just do? How did I accomplish that? Okay, so let me kind of take a diversion for a second here. Do you remember way back when you graphed sines and cosines? And what was the difference? The cosine graph started up at 1, and went like that. And where did the sine graph start? Well, the sine graph didn't hit 1 until pi over 2. A little sloppy here. So it went like that, right? So we have a shift. The sine graph was the cosine graph shifted pi over 2, or 90 degrees, to the right. And so when we graphed get these out of the way. When we graphed 1 theta, 2 theta, 3 theta, and 4 theta using a sine, what happened here? It was that circle, one petal, was rotated 90 degrees counterclockwise. When it was 2 theta, it was rotated 45 degrees counterclockwise. 3 theta was rotated 30 degrees. 4 theta was rotated, 22.5 degrees? So all we need to do, the only difference between the sine and the cosine rose graphs is 90 divided by n, or the coefficient of theta, gives us where our first petal was rotated up from the positive x-axis. And if we're in radians, that would be pi over 2 divided by n. So 1 theta, 90 divided by 1, are just 90 degrees rotated. Let's go ahead and back to our graph for a second. Let's just graph that one. Undo. So the circle is rotated up 90 degrees. When we have 2 theta, we wound up getting it rotated 90 divided by 2, which is 45 degrees, or pi over 4. Yep. And then when we wound up having 3 theta, it should be rotated 90 divided by 3, or 30 degrees, up from the positive x-axis. And so if I trace that, 30 is pi over 6. And there we go. And then the last one, if it was 4 theta, then the first petal should be rotated up 90 degrees divided by 4, or 22.5 degrees. And so it's rotated up 22.5 degrees, or since I'm in radians, what's that? Pi divided by 8. And sure enough, there we have it. All right, so when it's the sine, that first petal is rotated pi over 2, or 90 degrees if you're in degree mode, divided by n, that coefficient of theta, counterclockwise from the polar axis. And that gives us the summary of all our rose graphs. So now you still should be able to graph it by hand if you had to, making a table, but you should be able to pretty quickly know what the graph looks like if you're given the equation. Or if you see a graph of a rose, you should be able to write the equation yourself pretty quickly.